So we've been talking about the word mole and how it represents a number, just like a dozen equals 12. If we have a 6 followed by 022 and then all those zeros and condense it to scientific notation as 6.022 times 10 to the 23rd, which is also known as Avogadro's number, if we have that number of anything, we have 1 mole of anything. And we talked about in the last video about the hydrogen atom needing a mole of hydrogen atoms just to equal 1 gram on a scale. I want you to think about what a regular scientist has to do. We have to go into a lab and we've got a couple tools. We've got a scale for weighing out solids. We've got graduated cylinders to to measure out liquids, or maybe a pipette if it needs to be smaller. But we need amounts that we can actually see and feel and pour and transfer and work with. We're not going to be able to work with things that are so tiny that even just a dot in a book has 1,000,000 atoms in it. We can't work on the scale of atoms. And even if we start combining those atoms together, we wouldn't be able to work on a scale of the size of a molecule or just one compound, one molecule. So we have to start talking about things in larger quantities. And that's where the mole comes in handy. The mole is getting us large enough of all these teeny tiny things. When we have that many of them, we start getting on a scale or on a level that we can actually work with, that we can see and touch and transfer. So it is very important to scientists to be able to talk about things in terms of moles instead of in terms of just individual atoms. So as an organic chemist, I really had to do just a few different kinds of calculations every day. I had to work in terms of going from mass units, say grams, over to volume units, like milliliters, and go back and forth. And you may have already practiced things like that with density. That's our best way to get back and forth. Sometimes concentrations of things will help us to go from mass to volume. But if I wanted to go into a laboratory and measure out whether volume or solid mass, I needed to be able to know how much of each chemical I needed. And it's really hard when things weigh different amounts to work in terms of gram. I can't really compare directly the grams of one substance, let's say grams of carbon. It's going to be hard for me to do anything because trying to do an experiment or something in terms of grams of carbon and let's say grams of oxygen, it's not going to work in the lab. And that's partly because their atoms are different masses. The mass of carbon, of one atom of carbon we get off the table, is 12 AMU, atomic mass units. The mass of one oxygen atom is 16. So if I wanted one atom of this and one atom of that, I wouldn't be able to compare them in terms of their masses because they're not starting out the same. But I could talk about them in terms of moles because I could work with 1 mole, 1 quantity of carbon atoms combining with 1 mole, 1 quantity of oxygen atoms to make a molecule. So instead of talking about 1 atom combining with 1 atom, which I can't measure on a scale or in a pipette, let's talk about a whole mole of carbon atoms combining with a whole mole of oxygen atoms and making a mole of those molecules. And by working on that larger scale, we're going to be okay. But let's think about how that's going to work. We've been talking about all these masses so far in terms of the mass of 1 atom. But scientists also found that if we were able to take 1 mole of any of these elements, that the masses they had for their atomic masses would work, and I'm sure, I say they found this, I'm sure they worked this out to work this way, but would all these masses that are thought of as the mass of one atom would also work in terms of the number of grams, the mass in grams of 1 mole of the atoms. So if I were to take 6 gazillion, which I call the 6.022 times 10 to the 23rd atoms of carbon, ridiculously large amount, and stuck them on a scale, they would have the scale read 12.0 grams. And the same with another solid. Let's take sulfur. Let's take 6.022 times 10 to the 23rd atoms of sulfur. I stick it on a scale. Guess what? The scale is going to read 32.1 grams. So here's a great, gigantic chart filled with numbers for each element to tell us how much 1 mole of each element weighs. And we're talking large enough scale for me to be able to use this in a laboratory. Atoms and molecules individually are too small. I need larger quantities. I need something that's at least the 10th of a mole or 100th of a mole before I can start measuring it out, okay? So from now on, when you guys are looking at these numbers, these masses on the table that you used to think about in terms of atomic mass units for just one atom, I want you to start thinking about them as how many grams are in 1 mole of whatever element it is. 1 mole of atoms of manganese will weigh 54.9 grams. We call this the molar mass. The molar mass of manganese is 54.9, what are the units? Grams per mole. 54.9 grams per mole of manganese atoms. And what I've just done by combining 2 units like that, by saying 1 mole of manganese atoms has a mass. It's hard to write looking through a screen. 1 mole of manganese atoms equals 54.9 grams. And what's the rule? Anytime you have something equal to something, or per, or is, any sign that you have that there's a relationship between 2 units, you have a conversion factor. So I can write this information in the standard form of saying that 54.9 grams per mole, or 1 mole specifically, of manganese. I can also write this as 1 mole, and this time I'm going to abbreviate it. MOL is equal to 54.9 grams when we're talking about manganese atoms. Okay? So anytime I need to get from a mass unit into moles, or moles into mass, I have an entire periodic table with over 100 different masses, one for every element that I could use, every element that's working to make up everything I know and haven't even learned about in this universe. Their masses are right here for me to use. I never have to worry about finding a conversion between moles and mass, because I have it on the wall of every chemistry room I walk into, every chemistry book I open. I'm going to find this chart to help me out.